So we're going to investigate one more physics concept today, and that one is power. Right? We're going to take a look at the concept of power, very important for this course. Informally, the terms energy and power are often used synonymously, kind of like in the news media and such things. For example, your local electric utility may be installing wind energy units or wind power units, right? People will say the same thing. However, in science and engineering, the term power and energy are not synonymous. The term power describes the rate at which energy is converted from one form to another, or the rate at which energy is used, or the rate at which energy is transferred from one place to another. Since energy transfer requires work, power can also be described as the rate at which work is being performed. For example, the same amount of work is done when you lift an anvil 10 feet into the air, whether it takes you 10 minutes or 10 hours. So if I have an anvil on the ground and I lift it 10 feet in the air, that takes the same amount of work whether I did that in a day or whether I did that in a second. Same amount of work. What's different is the amount of power expended. The more power is expended during the 10-minute interval because the work is done in a shorter amount of time. This is typically expressed mathematically as power equals work over time. More useful for us as electrical engineers is a definition of power in terms of voltage and current. In a DC circuit, the amount of power supplied by a voltage source to a resistive load or a resistor is equal to the product of the voltage and the current. Power equals current times voltage, right? In a purely resistive circuit, all the power delivered by a voltage source must be dissipated into the resistive elements, which will result in the production of heat. Power is a scalar physical quantity measured in the SI unit of watts, named after the very famous James Watt. Power is a derived unit and can be defined in terms of the joule and the second as energy units divided by time units. So here we see that it's 1 watt equals 1 joule per second. Like energy, power is often measured in units other than the watt. The second most common unit of power you're probably all familiar with is the one used with automobile engines, the horsepower. And the conversion there is 1 horsepower equals 746 watts, about, I think. So let's do a quick example about power, and we'll refer back to that previous example with the hydroelectric pump. The pump used in the previous example is only 75% efficient, and we want to determine the electric power required to operate the thing for that 5 minutes. So what are we going to do? First, we need to determine the output power required to move the water. And remember, the equation is just power equals work over time. Well, we already calculated the work, right? Power isn't going to be from the work. It's 588,000 joules from the previous example. That's how much work was done. And in this case, we need to divide by 5 minutes. But hold the phone. On the last slide, I told you that power is joules per second, not joules per minute. So we have to put this 5 minutes into seconds if we want the answer to come out in watts. So what we now have to do is we have to multiply by, this will actually go in the denominator, excuse me. We have to divide by 60 seconds per minute, which in this case will be multiplied by 1 minute in 60 seconds, right? So all that is, this is just converting that, minutes over to 60 seconds. So what that results in is 1,960 watts. So that's the output power required to move the water. But remember, there's an efficiency rating of the pump. The pump doesn't convert all of the electrical energy into mechanical energy. We said that it had an efficiency of just 75%, which would actually be pretty good. So we need to calculate that. So the formula for efficiency, the input power is equal to the output power divided by the efficiency rating, eta, looks like a cursive N, And that makes sense, right? The efficiency of the system times the input power equals the output power. So if the system is 75% efficient, I only get 75% as much output power as input power. And so if I divide the output power by the efficiency, I get this input power. So 1960 watts divided by the efficiency, which was 0.75. Clearly, the input power has to be larger than 1960 watts, and indeed it is. It's 2,613.3 watts. And maybe I should just take the opportunity to point out the obvious. Efficiency ratings can never be larger than 1. You couldn't have an efficiency of 1.1. That would mean you would have more output power than input power.